All right. Hi, everyone. Today, we are very excited to have Christina Yu speaking our seminar. Christina is an assistant professor of operations research and information engineering at Cornell University. Christina holds a bachelor's in computer science from Caltech, master's and PhD both in EECS from MIT, and before joining Cornell, Christina was a postdoc at Microsoft Research New England. Christina is a 2021 recipient of the Intel Rising Stars Award and a JP Morgan Faculty Research Award, and her research interests include algorithm design and analysis, high-dimensional statistics, inference over networks, online learning, and sequential decision-making under uncertainty. And today, she's going to tell us about sequential fair allocation.
Great. Thank you, Saeed, and I'm really excited to be here. I really appreciate the invitation from the organizers. So I'll just dive right in. I did want to mention I'm really happy to take questions as we go. So please feel free to stop me at any point, ask questions to clarify. All right, so the starting place of our project was actually a collaboration with the Food Bank of the Southern Tier. And this is a food bank that serves over 21,000 people per week across 6 counties in the Southern Tier region of upstate New York. And in particular, they have a program called the Mobile Food Pantry that is relevant to our problem. And they distribute 3.4 million pounds of food in 2019, so over the course of the year, via this Mobile Food Pantries program. So let me tell you a little bit about this Mobile Food Pantries program. So what it is it's I believe they have 9 trucks that they load with food let's say at the beginning of the day, and they have a particular schedule of each day which locations are they going to visit at which time. So they might since they're the region that they support spans a very a fairly wide 6 counties in upstate New York. They might have like one location that they visit at 10 a.m., another location, at 1 p.m., another location at 4. So they have a particular route that's set, and they don't visit each distribution location every single day. So they might visit this location maybe once every 2 weeks, and in the neighboring county once every 2 weeks on a different day. So they load the truck at the beginning of the day. The truck kind of travels to location. Once it arrives at the location, then they can see how many people are waiting in line for the food, and they decide how much should I give to each person at this site. So the allocation decision is made in an online fashion where I see the demand at this location, and I need to decide how much to allocate before the demand at the future locations are realized. And
it's the same. Sorry, is it the same? The same type of food everywhere? It's not as if some places receive different food.
They do. So the truck is loaded with different types of food. And one thing we will actually introduce is that there are different types of individuals with different types of preferences. For example, there might be a vegetarian, there might be a family with a lot of kids, or where there may be different nutritional needs. And so you may not allocate the same thing to each location because the people who show up might actually have different preference types. Yeah, but the truck is the same truck. So it starts with the same amount of resources that's available to all locations. Yeah. Okay, so the demand is uncertain. However, we do have distributional information on the people that are arriving because of the history of that they collect of the past data. And so, an objective of the allocation would be to minimize waste, but allocate fairly across locations. I think in the general setting where you have multiple resources, different types of preferences, this notion of fair and what does fair really mean, needs to be carefully defined. And so, we can model our problem with a budgeted sequential allocation scenario where a principal is tasked with dividing K resources over T location, and each resource has an initial budget. And in every round, the principal observes the number of agents of every type that arrives at that location. and along with their preference vector, and the principal decides allocation of the resources to give to each type, and we will assume a linear utility. And after it decides allocation, the total resource consumption is just the sum of the allocation across the people who arrived in that location. And so in the resource allocation setting, there's the first question you need to answer is, well, what is the objective of your allocation? And I think so Sid already talked about this two weeks ago about the different types of allocation problems you might have, and settings where your goal may actually be to maximize. Some scenarios, your goal might be to maximize revenue or welfare. In our setting, with the mobile food pantry program, as I kind of suggested, the objectives we will care about would be to not waste any food. So that we'll refer to as efficiency. And also we want the resource to be shared fairly. And again, fairly, I haven't fully defined it yet, but colloquially you can think of it as, I don't want any agent to be envious or any individual to be envious of the allocation to another individual. And so to define fairness in the offline setting, when all of the, let's say when the demand is fully realized in advance, that has been very well studied. And so I'm gonna first give I'm gonna give a quick kind of a framing of the fairness framework we're gonna use, but Sid also did present on this a few weeks ago, so I'll go through this a little bit quicker. So in the offline setting, in the one-shot allocation setting, we have again n individuals, k resources, preference vectors for each individual, and again we're assuming linear utilities, and again budget constraints. So in this setting, there's three different perspectives we could take towards fairness. There's the axiomatic viewpoint where we specify different desiderata that we want a fair allocation to satisfy, and the two axioms we would desire are Pareto efficient and MV freeness. And there's an economic viewpoint where you could give everyone an agent an equal budget and let them decide, or an optimization viewpoint where you can choose an objective that you want to optimize for. And the beautiful theory that Halvarian introduced in the 70s was to show that, in fact, in the setting where divisible items and linear utilities, all these three different viewpoints are the same, that the allocation which maximizes the national social welfare, in fact, is also the outcome of the equilibrium for the Fisher market, as well as a solution that satisfies Pareto efficiency and NV freeness. And furthermore, because of the linear utility, the national social welfare can be maximized by maximizing a convex program, and the fair allocation is in fact unique. And in this talk, we're going to be focusing on the axiomatic viewpoint, but developing a theory in the setting of online sequential allocation. So how do we actually reason about fairness when you're now dealing with sequential allocations with stochastic demand? There's a lot of previous approaches to tackle this problem. The majority, in fact, are limited to single resource or single type setting because it's already difficult enough. and I think so. There's a couple different approaches. One approach is to focus on achieving ex ante guarantees on MV freeness, meaning that if I were to repeat this, repeat the setting many times, and I look at an individual agent and look at what's the expected allocation he gets, that the expected allocation is what they can kind of prove MV freeness with respect to. Unfortunately, the limitation there is that it doesn't mean that the actual allocation for a single realized setting is fair. And so even though you can have fairness over the expected allocation, the realized allocation could be very unfair. Another approach is to look at getting competitive ratio guarantees on the national social welfare. or additive guarantees. The limitation there is that it is not true that an allocation that is close to optimizing the national social welfare in the objective space, that it may not satisfy fairness, the fairness axioms that we would desire. So it might not actually be close to NV freeness, even though it could be close to optimizing the national social welfare. And another objective people look at are max min guarantees, but again, the results there are also only ex ante, so in expectation in advance as opposed to sample path based. So one critical question that was driving our work was we want to understand whether we can get individual sample path guarantees with high probability. So of course we know we can't get, with probability 1, you can't guarantee a fair allocation, but can we get some notion of, approximate fairness most of the time? And that's what we were really aiming for. So as a quick kind of sneak peek summary of our results, what we are able to show is that we achieve minimum, we minimize the additive deviation from an ex post Pareto efficient and NV free solution. So, in hindsight, after the allocation is fully realized, you look at what the optimal fair solution is, and we minimize the additive deviation from that ex post solution. And we're able to fully characterize the achievable trade-offs between Pareto efficiency and NV freeness that arises from the uncertainty in the demand. And we provide a simple policy that's based on ideas from a safe model predictive control that can achieve any desired points on this Pareto efficient and NV free trade-off curve. And our algorithms and results, in fact, do fully extend to the multi-resource, multi-type setting, which is the first that, at least that we are aware of, the first of these fairness, online fairness results that are able to handle multi-resource, multi-type. And we do also have some simulations on data generated from mobile food pantry data. And we, in fact, do see good empirical performance that matches what we are able to prove in the theory. So, all right, so to dive into the results in a little bit more detail, first, let's do a refresher on what the model is. Recall we have K resources, budget BK for each resource. We have agents of type theta, where we are going to assume a finite number of types. And we have linear utilities for the agents. And the key question that we first want to resolve is, what's the appropriate objective or metric for a fair allocation in the online stochastic setting? So to, again, just to set it up, recall what our ex post fairness definitions were. The two primary axioms were Pareto efficient and NV freeness. I also put here another desired property, which is proportionally fair, that any individual's utility is at least the utility that they would have gotten from evenly dividing all the resources. And in the setting where you have linear utilities, an allocation that is Pareto efficient and NV free also does imply proportionally fair. So as a result, we don't need to focus on the third one, the third property very much.
Can I ask a quick clarifying question?
Yes.
So I'm sort of hung up on the definition of NV freeness. Yeah. I'm not super familiar with this sub area, so this is probably very silly. But so I could imagine a situation where you have two customers, one person who's like a family of 5 and one person who's a single person, and maybe both of them would prefer to have as much food as possible. So like, but to be fair, you'd still give more food to the family than to the single individual. And so I'm just wondering how like that sort of notion of fairness is captured here.
Well, in fact, I mean, the nice thing about the national social welfare is that, in fact, the optimal solution for it is, in fact, scale invariant. And what that means, and I think maybe you can see it from this slide here, that because maximizing the optimal, the national social welfare, you can you can write it as maximizing the log of the national social welfare. And then if you scale and because we have linear utilities, if you scale it, then the scaling factor just comes off as out as an additive constant. So it doesn't end up affecting the final fair allocation. So in this sense, it kind of, I guess that's also a nice property in that it doesn't depend on the scaling of how your utilities are defined. Maybe that's a partial answer.
Yeah, I'll keep thinking about it, but yeah, thank you so much.
Yeah.
Wait, let me, because I have maybe a similar question, so let me try phrasing it differently. So like, I know that like national social welfare is like invariant to the units in which you're measuring welfare, but Ira's question seems more related to like the boundaries we draw around agents. So if I'm coming to the food bank for, on behalf of a family of 5, it seems like you sort of want to treat me as 5 people. And
I see what you mean.
if you're treating me as 1 person, then the allocation might not be NV free because it looks like I'm getting 5 people's worth of food.
That is a good point. I see what you mean. So I think maybe we would need to take that, like if on a actual practical modeling perspective, probably you would want to model, let's say if a family of 5, that they would probably want to model it as, as the 5 individuals where where maybe the children actually have different type preference than like the parents because they have different nutritional needs. So if you have heterogeneity in the family too, you would, yeah, I think here we're really only getting we're assuming that each individual is like 1 individual and we're doing fairness individual based. So I think with a family, you would split it into individuals and then any heterogeneity in the individuals you would model with their types.
I see, that makes sense. And then
thank you for the
your remark about children makes me think of another question about the modeling here, since I just took a bunch of them trick-or-treating. But like, oftentimes, I guess children, my children at least, would express utility for very large amounts of candy, like more than an adult, even though they are very small. So presumably in the modeling here, you're sort of assuming that like children eat less than grown-ups. So like somehow in the modeling, you would like be capturing that in the utility functions, and instead of saying, oh, well, my children are like envious of like this family of 5 because they want as much candy as the family of 5.
That's a good point. Yeah, I guess it is implicit that is modeled by the weights vectors. And that, I mean, that like if you scale, well, yeah. So yeah, I think there is some assumption that the weight vectors are kind of
okay. Like, I guess the bigger question is, where do the utility functions come from? And is the answer that you're just taking them as given in this model?
Yeah, we are just taking them as given in this model, but that's a really good question. Yeah, so that's a good question. We
okay.
really consider any questions around like, strategic utility or, revealing. So we assume that they're given. Yeah, thank you. All right, well, thanks for the questions. I appreciate them. So, all right, so in the ex post setting where all the demands are realized, we can find this unique ex post fair allocation by maximizing the national social welfare. And the Eisenberg-Gale program is the program for maximizing the log of the national social welfare. So, and in fact, well, it's fairly natural to see that no algorithm can actually guarantee, with probability 1, a fair allocation on a stochastic model, just because of the uncertainty in the future demand. And so we're gonna introduce a few definitions for approximate fairness. And so in the online setting, what we're gonna want is we wanna find an allocation which has low well, I'm going to call it delta efficiency, which is distance to an efficient solution. This is going to be equal to the waste. So in our setting, because with linear utilities, the distance to efficient solution would just be the amount of waste that you have. So this is the sum over all resources of the budget you have minus the amount that's allocated. And the second definition is NV, and this NV would be, you know, for some allocation that is realized, what's the, NV that is between any two individuals arriving in any location. So you can allow individuals to NV across locations as well as across types. And so I'm going to actually introduce one more definition, which I'm going to call delta EF, or distance to an NV-free solution, or counterfactual NV. So here I've kind of distinguished the previous NV definition I defined. I'm going to call it hindsight NV. So it's the NV in the realized allocation. This counterfactual NV, or delta EF, is going to be the distance in the utility space for the individual that they achieve, they receive from their own, from the algorithm, minus the utility they would have received in the optimal offline allocation. So again, X-opt is the solution when all the demands are realized so at the end of the time period, after all the demands realized, then X-opt is the solution that you wish you could have allocated. And so this counterfactual NV is, you know, how much is the agent kind of missing out from what they were supposed to have gotten if you didn't have stochastic demand. And I think I want to make a few points. One is that the way we're measuring up the approximate fairness or the unfairness is measured with respect to the axioms on fairness, as opposed to approximating the national social welfare objective. And I mean, that's useful because these axioms are in fact the desiderata that we actually want in our fair allocation. Furthermore, it's important that we require both Pareto efficiency and approximate Pareto efficiency and approximate NV freeness, as it's easy to satisfy both in isolation. So I can get an efficient solution by giving everything to one person. I can get an NV freeness solution by giving nothing to anyone. But so you really need both of these two objectives. And the last point is that the reason why we introduced this third counterfactual NV is because, in fact, if I can prove that the allocation has a small distance to the optimal offline allocation in utility space, then in fact it implies a bound on my hindsight NV as well as my waste. So in particular, this this counterfactual NV, even though it's not one that is actually realized, is actually going to be very useful for the development of this theory and the algorithms. So any questions about the definition, since we'll, okay, great. So again, just to give intuition for why these three approximate unfairness metrics are important. Delta efficiency, you want that to be low to ensure the resources are used to limit waste. NV, you want to be low because you want to promise individuals to have low NV in the actual realized allocation. And then you want delta EF to be low because you want to promise individuals that they will receive as much utility for their online allocation to what they should have gotten in the counterfactual offline fair solution. Okay, so this is the one picture slide for our result. And what we're able to show is that, in fact, under mild conditions on this demand distribution, the variable process, that we can, in fact, exactly characterize what is achievable in terms of the trade-off between efficiency and NV. So here the x-axis is plotting delta EF. So that's the distance to this is the counterfactual NV, distance to the offline optimal. The y-axis is plotting delta efficiency. So think of that as the waste. So the first part of our result is a lower bound that says any algorithm has to suffer distance to so delta EF of on the order of t to the -1/2. And here it's saying any algorithm must suffer this with with constant probability. And the second result is saying any algorithm must suffer this delta efficiency bounded by 1 over delta EF. So depending on what you're willing to tolerate in terms of your distance away from an NV-free solution, it's going to affect the bound you can get on the amount of waste that you can achieve. or that you can, the max waste that you can achieve. And this green region on the top, in fact, is the achievable region, and we're able to provide a very simple algorithm that in fact can achieve any point along this curve here. Questions?
I have maybe a dumb question.
Yeah, no, please ask. There's no dumb questions.
So like I'm trying to figure out why time is the right sort of quantity to measure. Is this sort of mediating some implicit like large market assumption? Like as time gets bigger, are we sort of implicitly like making the truck bigger and the amount of food each person eats is like smaller relative to the size of the truck?
Well, okay, I think the reason why time is the critical piece is because it's the thing that's governing how much uncertainty, as well as how much, like what's your time horizon that you have to deal with that uncertainty, if that makes sense? Because there's uncertainty in the future, and you also have, that's also the time you have to kind of smooth out your allocations relative to the certainty. So if your time horizon is really short, like
I'm trying to figure out why the problem becomes easier if I have a really long time horizon, but I don't have more food.
Sorry. Okay, so what we assume is that kind of the budget scales proportional to the expected demand.
I see, and that scales in proportion to time.
Yes.
I see. So it's maybe like, so like the x-axis is really making the truck bigger.
Yes. Yeah. I mean, I think the other way to think about it is if you are in the limits of like the budget divided by total expected demand is nothing, then, or in the other limit where like the budget divided total expected demand is like super huge, then the problem also is kind of easy. Because you have nothing, then you just kind of, the best you can do is like already limited by the nothing that you have. So actually the difficult regime is where the budget matches the expected demand, which scales with T. Yeah, thank you. Great clarification. Okay, so on the positive side, so the previous plot, I guess it was highlighting the lower bounds. On the positive side, we provide this algorithm called guarded hope, which does achieve this optimal trade-off between the NV freeness and efficiency. In particular, it's parameterized, so you can achieve any trade-off that you want on this curve. And we have a bunch of simulations that show our algorithm in fact does well and does in fact exhibit this trade-off. I'll kind of explain the simulations maybe when we get to it at the end again. So, but the punchline for this picture is that our algorithm in fact does well. They're the three curves on the bottom here and on the bottom here, or not on the bottom here. So on the three curves on the bottom here, and then you can see that the middle plot is the waste. The first plot is the NV freeness delta EF. And what we have is that if you tune the parameter of the algorithm, you can trade off between either having a higher waste but lower NV freeness, or so lower distance to NV freeness, or higher distance to NV freeness but then lower waste. Okay, so here's the main theorem, and so I guess as Aaron actually was pointing out, we do have an assumption that suppose that your budget is on the order of the expected demand. Under some mild regularity conditions I'll mention next, we have first a statistical uncertainty principle that says because of the uncertainty in the future demand, no algorithm can achieve can guarantee that the delta EF is bounded away from is smaller than 1/√T with constant probability, so that this has to be scaling at least as 1/√T. And then the second part is that the waste has to be at least 1 over this quantity at delta EF. We also have it characterized in terms of the actual realized NV as well. And the only difference here is that you can actually achieve realized NV of 0 by giving everything the same thing, by everyone the same thing. So that's why there's this additional kind of min here. And then the third part is that we do achieve it with our algorithm. And in fact, for this parameter LT given prior to our algorithm, our algorithm achieves the NV bounded by LT, achieves the delta efficiency bounded by LT as long as it's larger than 1/√T. And then delta efficiency indeed is also bounded by right scaling. So let me tell you a little bit about what the assumptions are, which are important. So the first two assumptions on the preferences are that there's a finite set of types, and second, that we have linear utility functions. This can be slightly relaxed to homothetic utility functions, but it is heavily because we are relying on a relationship to solving the Eisenberg-Gale program to relate the optimal offline allocation. And the assumptions we have on our demand distribution is that the demands are independent across time and across type, that demands are bounded, and that we have a bounded variance, both bounded below and bounded above. These assumptions can also be slightly relaxed. The primary condition we need is that we need to be able to construct confidence sets with high probability on the future demand. So this is where we're using the distributional data, the distributional assumption that comes from having historical data. And so, I mean, these assumptions can be slightly relaxed to say sub-Gaussian demand instead, demand that evolves as a Markov chain, or where it's slightly, the demand is dependent, but it's dependent only, the dependency is only governed by a latent variable. Okay, any questions about the model and the overarching results before I move forward? Okay, great. So let me give some intuition for what the result is. I'll just get the intuition in the single resource, single type, and IAD bounded demand setting. And as I mentioned, it does extend to multi-resource, multi-type as well. And so in the single resource, single type setting, it's a lot easier to look at what the objective is. Because we know what the, let's see, the optimal offline is just going to be a scaling of B over N. So we're just going to assume the preference is just, the linear preference is just weighted by 1. So because it's just a single resource type. So our optimal allocation is just splitting the resources uniformly across all the individuals. And so this delta UF, the distance to what you should have gotten in the counterfactual offline solution is just the distance away from this, the total budget divided by the total demand. Again, this total demand though, N is uncertain, it's a random variable. And then the efficiency again is the waste, right? This delta EF is the waste. So the first result is that any online allocation must suffer delta EF greater than 1 over root T, at least with constant probability. This one is straightforward to show, and it follows from the statistical uncertainty in the future demand. And so why this 1 over root T? Well, if you think about the very first allocation, at the very first location, you need to commit to what you're allocating to that first location before you see anything in advance. And once you've committed to that first allocation, then your distance to NV, the optimal counterfactual offline solution, it has to be at least whatever you allocated to the first person, the first round, minus B over N. But now you can look at the distribution on N and argue that because the variance is bounded away from 0, we can show using Berry-Esseen and anti-concentration results to say that this distance has to be with constant probability at least 1 over root T.
And in the model, when you assume the lower bound on variance, is that only needed for the lower bound, or do the upper bounds also?
It's only needed for the lower bound. Yeah. So
got it.
Only needed for the lower bound, indeed. Thank you. Okay. So the second result is that we have a lower bound also on the waste. So this and the waste again is related to what's your bound on the distance to an MV-free solution. So there's a trade-off between the two. And as an example of what this trade-off means, it means that if the minimum, recall the minimum bound I could have on this distance to this counterfactual NV is 1 over root T. And so if I want to achieve delta EF of 1 over root T, then I have to incur waste of root T. But if I want to incur less waste, I can relax that constraint on my counterfactual NV. So for example, if I bound counterfactual NV just by T to the minus 1/3, then I can get waste bounded by T to the 1/3. And if I allow a constant delta EF, so constant counterfactual NV, then the waste can be constant as well. Okay, so to give some intuition of where this relationship between MV and efficiency, the lower bound, comes from, suppose you actually have an allocation algorithm, which needs to guarantee with high probability that, or at least with a large enough constant probability, that the distance to NV free, so the counterfactual NV, is less than or equal to some parameter LT. Then that means your allocation needs to stay within this interval of whatever the optimal offline allocation is, plus or minus LT. And do keep in mind this xopt is a random variable. So the algorithm, because it needs to guarantee that you're always able to satisfy that the allocation lies within this bounds, the kind of worst case scenario is that the algorithm accidentally gives out too much resources up front and runs out so that it has to give 0 to people at the end. Then it's not able to realize this bound on the counterfactual NV. So as a result, the algorithm, because of this bound on the counterfactual NV, the algorithm has to be conservative, and it has to ensure that the remaining budget after each round is enough to guarantee at least x opt minus LT to the future individuals. So meaning that I need my budget BT, so I should think BT here, you're referring as the remaining budget at time t. It has to be at least the lower, this x opt minus LT, so the lower threshold of this interval of allocation, times this upper bound on the future demand. And think of this, it's not only an upper bound on the future demand, because the variances are bounded away from 0. If you choose the appropriate constant in front of the square root, then with constant probability, the demand is actually larger than this value too. And that's in fact the tension that arises, in that we have to be conservative enough to make sure we have enough to not run out if a lot of people arrive. But the unfortunate part is that with constant probability, there's also the scenario that too little people arrive, which means the amount of people that arrive is on the lower part of my confidence set. So the expected demand minus root t minus t. So this is the amount of time periods remaining. And in the case when too few people arrive in the future, because of the constraint on our counterfactual NV, we are not allowed to allocate them more than x opt plus LT. So because our allocation to satisfy this bound on counterfactual NV, since it has to lie in that interval, we can't allocate more than a certain amount. But then, but in the event there's too few people and we can't allocate a certain amount, then that means you're going to have a waste of at least, however much you are conservatively saving in your budget, minus the most that you could allocate when not enough, I guess fewer people arrive in the future. And so that results in a waste of, this expression where it's x opt times square root of the time periods remaining minus the expected demand in the time periods remaining times LT. And so it turns out that when you're looking, so if you choose little t or t minus t little t to be 1 over square root LT, so 1 over LT squared. So in the last 1 over LT squared rounds, this bound on the magnitude of your control. So the fact that this counterfactual NV bound bounds the amount of control you're able to have with your allocation, that it kind of makes your control insufficient to offset the statistical uncertainty in your future demand. So that's what these two terms are. And so as a result, it implies that your waste has to be at least 1 over LT with constant probability. Okay, any questions about this MV efficiency and uncertainty principle before I move forward? Okay, and so I think what's really interesting about this is that really this trade-off is arising, again, is rising because of this uncertainty in the demand, and not due to a bad algorithm in any way, like as in there's no algorithm that can really achieve better than this, because it's really a fundamental information theoretic lower bound that arises from uncertainty. All right, so just to refresh what we showed, the intuition we've showed so far is that we showed that this red strip here, that the because of the uncertainty in the demand, you and you're forced to allocate in the very first location before seeing the rest. Your delta EF can't be less than 1 over root T. And then the second part here, this curve here, is the lower bound on the waste relative to the bound on the counterfactual NV. And this arises again due to this tension between needing to be conservative to make sure that you can actually satisfy the bound on counterfactual NV, but then also the worst case scenario where too few people arrive in the future and your control is limited. Okay, so next I'm going to tell you about our algorithm that achieves this region in green. So our algorithm is called guarded hope, and it's actually fairly straightforward. Given any parameter LT, which is a parameter bounding the MV, we construct a lower guardrail and an upper guardrail, and our algorithm actually allocates within these two guardrails in order to guarantee the NV. So how the lower guardrail is constructed is by generating a pessimistic allocation by replacing, we solve the Eisenberg-Gale program, but replace the demands with this high probability upper bound on the demand. So I call this a pessimistic allocation because I'm saying, well, conservatively, what's the most, with constant, with reasonable probability, what's the, upper bound on how many people might arrive, and if that many people arrive, how much would I allocate? So this is a X lower bound, X lower. For a single resource type, again, it's just the budget divided by the expected demand plus root T. The upper guardrail is generated by solving the Eisenberg-Gale program with an optimistic lower bound on the demand to guarantee that this NV is bounded by LT. So in the simple setting with our single type, single resource, then you can just think about setting this upper bound, X upper, to be the lower bound plus LT. And so one part of the work for the proof is to argue that with high probability, this optimal offline solution does lie within these two guardrails as long as this parameter is at least 1 over root T. And this comes from proving results on the sensitivity of the outcomes of the Eisenberg-Gale program relative to perturbations in the demand. So, so the algorithm, again, it's built off of guardrails that are that govern, that define intervals that the algorithm respects in an allocation. And a naive allocation is to say, well, I'm just going to always be conservative and always allocate according to the lower threshold, just to make sure I never, I don't accidentally run out of budget, and not if I run out of budget, that's the worst case, because then I can't even satisfy my bound on the counterfactual NV. But this is in fact not it does not in fact achieve the appropriate scaling, except for when you choose this parameter LT to be 1 over root T. So what algorithm does is in fact a slight variant of it, which is a natural one. Why don't we just allocate according to the upper, so anytime that we can ensure enough resources to allocate the lower conservative amount to everyone in the future, and we have enough to allocate the upper amount to the individuals in the current time period, then we'll allocate the upper one. Otherwise, we'll allocate lower. So what this is doing is it's kind of using the conservative policy at minimum, and then it looks and at the budget it has, and if it has enough budget to be more aggressive and allocating X upper bar, or to be more generous, I could say generous and allocate upper bar, but still guarantee enough to satisfy everyone's needs at a minimal level in the future, then I'll go ahead and be more generous now. So questions about the algorithm? Well, actually, I have the summary of the algorithm here. Any questions about the algorithm? So you can see that the algorithm is actually really easy. You solve a convex program, twice in the beginning, once or twice in the beginning, and then the allocation rule is actually, really nice, really simple. But it turns out that it's the right thing to do. It does achieve, so by construction of these guardrails, it does achieve that the NV is bounded by LT, and this counterfactual NV is also bounded by the appropriate LT or max of LT and 1 over root T. And so you can show this by, again, the concentration of the optimal offline solution using a sensitivity analysis of the Eisenberg-Yale program. And then the second part is that we want to argue that the waste of the algorithm, in fact, is also minimal. So it achieves the correct trade-off between the waste and the counterfactual NV. And this arises from arguing that the budget, so anytime that you allocate the lower threshold, it means that the budget is tight, meaning that because anytime you, I guess I'll go back to the algorithm to see, so that anytime you have enough to allocate the upper threshold now and the lower threshold to everyone in the future, then you go ahead and allocate more generously. And so anytime you're allocating the lower threshold, it means that your budget is not too large. It means it's just about at the right threshold it's just enough to allocate the lower threshold to everyone. And so, because the budget is kind of tight anytime that the lower threshold is allocated, then next we want to argue that there has to be a time within the last 1 over LT squared times for which the budget is tight. And as a result, the waste cannot be too large at the end of the time period.
And let me understand why there's waste, because you're explicitly like throwing away food at the last stop instead of giving it to the last person so that you can get the NV freeness bound?
Yes.
And is that a credible policy? Like, can you instruct the food bank to like throw away food instead of giving it to the last food bank? And if not, is that a problem for the NV freeness?
Right. That's a great question. I mean, I would say that what you can do is you would probably want to trade off between, like, figure out what's the comfortable point on the trade-off curve, and in particular, the best. So if they really don't want to waste any food, then what you would do is it means that you have to incur a constant bound on a constant NV, which maybe constant NV is not too bad, right? It means that how much I'm envious of someone else does not, it doesn't scale with T, is constant. As opposed to, right, the other choices would be as T is large, how much I'm envious of someone else goes to 0. Like, let's say 1 over root T or 1 over N T to the 1/3, right? Those NVs will go to 0. But if I'm willing to tolerate constant NV, then you can get constant waste. In fact, constant, you can get 0 waste.
Yeah, I guess it would lead to interesting incentive problems, because I might want to, depending how the algorithm works, show up last.
Yeah, that's also a good point. In fact, so I don't have the we don't have it included here yet, but we also did look at kind of what would be the unfair, like empirically we looked at like what's the expected unfairness relative to where you arrive in the location, like in the beginning or the end. And I think one thing you can do to remedy it would be that you like kind of change the direction of your route. So you travel in one order the one time that you allocate, and the next month you travel in the opposite order. I mean, okay, if the order is publicized, then I guess people will still strategize. So I guess it needs to be a random, you flip a coin and with random probability, either travel in this direction or that direction.
Yeah. I mean, a less socially responsible setting in which this seems also like a good model is I guess some of these NSF programs now have like rolling deadlines, but they've got a budget for the year, and so they have to figure out how to fund grants as they're coming in, and like you might want to figure out, do you want to submit your grant like towards the end of the fiscal year because they'll have money left because they're doing something like this, or will they have run out? Do you want to do it early?
I see. I mean, I think what we saw in the experiments is that like the people at the beginning actually get the higher budgets more consistently. The people at the end sometimes get higher budget, sometimes get lower budget, but the people at the beginning kind of always get the upper threshold. And so I think one thing that we also played around with empirically was kind of, you can slightly change the because the
Sorry, did you, when you did this experiment, was it with this algorithm that throws stuff away at the end, or was it with an algorithm that gives everything away?
We actually tuned our algorithm. We used our algorithm for different choices of LT. So we did, we did it for the settings where you do throw away at the end. You do throw away.
Right. Because I guess if you don't, that might make the last position pretty good.
Yeah, the last position will be super, super lucky.
Yeah.
Yeah, that's right. Yeah, no, thank you. Okay, so okay, well, next we'll talk about the experiment. So what we did is we chose the budget to be on the order of the expected demand. So, and I think this in fact is the most difficult regime where the results are most difficult anyway, so it's most interesting here. And we had a synthetic setting where we generated demand from a Poisson distribution. We looked at 5 different types, 3 different types of resources, and we kind of we picked specified a fixed preference vector for each type, and then we also ran kind of like experiments based on that are motivated by food bank data. They're also generated. They're also kind of synthetic in that we took. So the food bank data we have is not granular enough to see actual demand at in different days on each locate or of different types. So all we can only see kind of aggregates over different counties of how many for different counties how many people did they serve, and so we fit a Gaussian where we just set the mean according to the means of the historical data, and we have again 5 types 3 resources. The preferences are not from the the food bank data isn't granular enough to show different types of individuals and preferences. So we just constructed preferences from prices in the food pantry distribution market. We compared our algorithm with 3 choices of LT. So 0, t to the -1/2, and t to the -1/3. And we compared it against 2 heuristics called Hope Online and Hopeful. And these heuristics solve the Eisenberg-Gale program. So the Hope Online solves the Eisenberg-Gale program for the remaining time steps by replacing the unknown demand with the expectation. So this is a model predictive control algorithm. And Hopeful at each time solves the Eisenberg-Gale over the full time horizon and replace the unknown demand with expectation, but it ignores the past allocations. So here we'll kind of show what the experiments look like. The top one here, the pink on the top is Hopeful, the orange on the top is Hope Online. So you can see that Hopeful and Hope Online actually had pretty poor counterfactual envy. Our algorithms, the green line is the choice of LT equals 1/3. The orange line is choice of LT equals 1/2. And the blue line is LT equals 0, which is a fixed threshold. So you can see if you look at the ordering, I guess between the first and second plots, is that indeed we see the relationship that when you have higher counterfactual envy, you can get lower waste. If you have lower counterfactual envy, you have to incur higher waste. And the plot on the most right-hand side is we took the distance from the counterfactual, the absolute value of the distance from the counterfactual, or not the absolute, sorry, the distance from the counterfactual, and then we averaged it across multiple simulations. So this is kind of looking at in expectation, how much does my utility deviate from my expected offline utility? And so you can see that people in the beginning are, in our algorithm, people in the beginning are much happier, they get a better outcome than the people later. So there is some kind of ordering. It might be subject to some strategic behavior, which would be interesting to look into. The second set of plots is from the food bank simulated data. The scaling is a little bit makes it hard to see because the Hope Online actually is very noisy, and so you can see it kind of the noise dominates. But in fact, the ordering with respect to the other algorithms, in fact, matches the similar results we see in the synthetic setting as well. So yeah, so in conclusion, we are able to show both tight lower bounds and upper bounds for the optimal trade-off between NV and efficiency, along with a very simple algorithm that achieves any point along this trade-off curve. And I did want to, again, emphasize that the results hold, these guarantees hold with high probability in the multi-resource, multi-type setting, which I think, we're really excited about just because it is able to generalize to a more complicated setting, but even get stronger guarantees in a sample path sense. And some future directions we have is I think we're really kind of excited about this overall framework of thinking about information theoretic trade-offs that might arise in general for fairness and efficiency in other scenarios when you have online stochastic demand. And we also be interested to characterize these similar information theoretic trade-offs that arise in other multi-objective scenarios in societal applications of ML. And we also have kind of in progress work looking at fairness in the inventory supply chain setting, where you might have your supply is also stochastic in arriving over time. Thanks, I'd be happy to take any questions.
Thanks for the great talk, Christina. If there is any question, people can unmute themselves and ask.
If nobody else has one, I have just a question about the process of collaborating with a food bank.
Oh, go ahead. And Moni also had a question.
Why don't we, let's take the real questions first.
Oh, was that a question? Sorry, or maybe it wasn't. Oh, go ahead, Aaron.
So thanks for the great talk. So you've developed this algorithm and proven this theorem. So what does the food bank think of this? Do they enjoy do they enjoy theorems? Are they gonna implement this on their trucks? What's happening?
That's a great question. I mean, so this part of it is still under conversation. Actually, what happened was that this work really happened during the COVID time, and the food bank was super stressed and volunteer understaffed for so they haven't really had the extra bandwidth kind of to explore further on. So we have not yet kind of been able to move forward in terms of practically getting it implemented, but that is definitely, I should put that in as part of the future directions as well, is definitely following up on those conversations there. I think now may be a good time, kind of we're waiting for them to for their operations to stabilize.
And did this arise from a problem they told to you? Did they say gosh, we're allocating all of this food, but we're worried that we're doing it unfairly, or people are expressing that they're envious of the other food banks, or
well, they do see, I mean, there's actually other projects that came out of these collaborations where they are actually interested in other questions that arise are, even how should you schedule your routes? In particular, they actually do see individuals making, I'm not sure, strategic decisions, but decisions okay, well, they see people's behavior that, let's say, if it was rainy on the day that the distribution was at the location I usually go to, then maybe I'll wait for the next good day that the neighboring site will have a distribution, and I'll go there instead. So they do see people kind of changing up where they show up. I mean, and there was another project where they actually kind of if Sid's here, he can jump in, where they're actually kind of building an app to help the food bank help with their operations there too. But I think the fairness part of it does come out as explicit objective because of where their funding comes from. So the when they get funds from like the larger, let's say Feeding America program, they do need to report records and statistics of how they serve different populations in different locations. And so they do need to show that they are kind of being fair, at least in a vague notion, again, probably not in a precise notion as we define here. So that is an explicit kind of goal that comes not just from them, but from their funding sources, actually.
Cool, thanks.
Looks
So
like
I just have
Judy,
a question. Yeah. So I guess like in terms of maybe a bunch of food banks, they have participants fill out when they will plan to show up before. And so I'm just wondering, like, because this issue of fairness gets a bit complicated because as you're handing stuff out by the end, there's people who didn't sign up who are like, oh, but I've been waiting here for a long time. So these questions of wait time, or like, can you just directly scale this budget that you've presented by the remaining food and then assume a stochastic model? Or it's hard to say because then some people did sign up, but then don't show up until it's free for all time.
I see what you mean. That's a good question. I mean, I think it would be an interesting variant to look at. If part of your demand was already fixed in advance, but then you had, I don't think that would change too much. Like, I think our model will be able to handle it. And the reason being, you can think of our distribution on a demand where there's a fixed amount plus a stochastic shift, and that would govern your distribution. And so you could model that in here as well, and it would just change the way that you construct your confidence sets. Yeah, thanks.
All right, I guess let me finish the recording.
I also